All right, today in geometry, we are looking at section 10.4, inscribed angles and polygons. We're going to get some vocabulary out of the way first. So first, we need to talk about what an inscribed angle is. So an inscribed angle is an angle with a vertex on a circle and sides that contain chords of the circle. The arc that lies in the interior of an inscribed angle and has endpoints on the angle is called the intercepted arc. All right, so in this picture, we see that this angle is the inscribed angle. So the vertex is on the circle itself, and then each of the sides of the angle are chords. This arc that's between those two chords is called the intercepted arc. We have some theorems that deal with these. So the very first theorem says the measure of an inscribed angle is half the measure of its intercepted arc. Okay? So in this picture, the measure of angle ADB is half the measure of arc AB. So the arc is always bigger. So like if this arc was 4, then I know that the angle would be 2. It's half of it. All right. Theorem number 2 tells me that if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So if I look at the inscribed angle ACB, it intercepts arc AB. Angle ADB is also inscribed angle, which also intercepts arc AB. Then I know that the angles are congruent. So then I know that angle ACB is congruent to angle ADB because they have the same arc. Next, we're going to talk about polygons. A polygon is an inscribed polygon if all of its vertices lie on a circle. The circle that contains the vertices is referred to as a circumscribed circle. So here we see we have an inscribed triangle because the 3 vertices are on the circle. Here we have an inscribed quadrilateral because the 4 vertices are on the circle. So those circles will be called circumscribed. Another theorem, if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. The converse of that is true. If one side of an inscribed triangle is the diameter of a circle, then the triangle is a right triangle, and the angle opposite the diameter is a right angle. So in this picture, if the measure of angle ABC is 90, then we know that AC is the diameter of the circle. Theorem number 2, any quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Remember, supplementary means adds together to equal 180. So in this picture, it says A, B, C, and D lie on circle E if and only if the measure of angle D plus the measure of angle B, so opposite angles B and D add together to equal 180 degrees, and opposite angles A and C add together to equal 180 degrees. So now we're going to use all of those theorems that we just talked about to solve some problems. So the first example says find the indicated measure of circle P, the measure of angle T. So the measure of angle T right here, I see I have angle RTS is inscribed. Its arc is 48. So my angle is half of the arc of 48. So half of 48, 24 degrees. Next, we want the measure of arc QR. So arc QR is this arc up here. I see angle QRT is inscribed at 50. And so I know that that means this arc is 100. I know that this is a semicircle. which means it has to add together to equal 180. So if this part is 100, this part is 80, and that's what we were looking for. So that's 80 degrees. The second example over here, find the indicated measure in circle C, the measure of angle D. So angle D is that inscribed angle up there. The intercepted arc is 100, so the angle is half of the arc. So half of 100 is 50 degrees. Now we want arc AB, the measure of that. So again, I know that this angle down here is 35. So this arc is double that, so 35 times 2 gets me 70. So I know that this arc is 70 degrees. I know that this is the diameter, so together it has to equal 180. So 180 minus 70 leaves me with 110. So this is 110 degrees. Next example down here, find the measure of arc RS and the measure of angle STR. What do you notice about the angle STR and angle RUS? So first let's look at the measure of arc RS. So that's this arc right here. I see it is intercepted from this angle. So I know that it is twice that angle. The angle is 31. So 2 times 31 is 62 degrees. So now I want the angle STR. So STR. So the measure of angle STR. If this arc I just found out was 62 degrees, and I want this angle, I know it's half of that. So half of 62 gets me back to 31 degrees. So what do I notice about those two angles? I notice that angle STR is congruent to angle RUS. They are equal to each other. All right, let's look at our last page. It says find the measure of the red arc or angle. So we're looking for angle HGF. It's an inscribed angle, so I know that it's half my arc, so half of 90, 45 degrees. This time I'm looking for arc TV. It is double my angle, so 2 times 38 gets me 76 degrees. Here I'm looking for this angle right here. I know it's going to be half of this arc. This angle intercepts the same arc, so I know that that's 2 times 72 out here. But remember, we had the theorem that told me that if two angles intercept the same arc, then the angles are congruent, so I know that that angle is 72 degrees in there as well. So now we're going to look at some inscribed polygons. Find the value of each variable. So I have x and y over here. Q, R, S, and P, all those points are on the circle, so I know it's inscribed. So that means my opposite angles have to be supplementary. So in this first one, 80 and x are opposite. So 80 plus x has to add together to equal 180. And x has to be 100 degrees. Y and 75 add together to equal 180. So then y has to be 105 degrees. Come over here to B. Again, I have this quadrilateral, looks like a kite, inscribed. So I know my opposite angles, so 2A and 2A are opposite. So they have to be supplementary. So 2A plus 2A has to equal 180. So then I get 4A is equal to 180. And so A is equal to 45. 4B and 2B are opposite. So 4B plus 2B have to add together to equal 180. So 6B is equal to 180. So B has to equal 30. Come down here to number 5. Again, I have a inscribed quadrilateral. So my opposite angles have to be supplementary. So x plus 82 has to equal 180. Subtract 82 from both sides, so I get x is equal to 98 degrees. Y and 68 are opposite, so y plus 68 has to equal 180. Subtract 68 from both sides, and I get y has to equal 112 degrees. Come down here and do number 6, and then we'll look at the two word problems. Again, I have an inscribed polygon, so I know my opposite angles have to be supplementary. So c plus 2c minus 6 has to equal 180. So combine like terms, so I get 3c has to equal 186. So c has to equal 62. And that's going to be the angle itself, so degrees. So now I would say 10x plus 8x equals 180. Combine like terms, 18x equals 180. Divide by 18, x is equal to 10. All right, so let's look at this first word problem, photography. It says your camera has a 90-degree field of vision and you want to photograph the front of a statue. You move to a spot where the statue is the only thing captured in your picture. Okay, so this is the statue right here. You want to change your position. Where else can you stand so that the statue is perfectly framed in this way? So if we look at this, this right here is going to be my diameter. If I draw that semicircle, then any point on the semicircle in front of the statue should fit within a 90-degree field of vision. So like if I came here and if I came over here, all of these should be 90-degree angles. So any point on the semicircle in front of the statue fits within the 90-degree field of vision. That comes from this theorem right here that says if a right triangle is inscribed in a circle, the hypotenuse is the diameter of the circle. So diameter is my hypotenuse. So any right triangle I make anywhere I stand, so again, as long as that diameter, so if I stood right here, that's going to be a right triangle. So any of these spots along that semicircle are going to fit into that. All right, our very last one says, suppose three moons A, B, and C orbit 100,000 kilometers above the surface of a planet. Okay. Suppose the measure of angle ABC is 90 degrees, and the planet is 20,000 kilometers in diameter. Draw a diagram of a situation. So I'm going to say I have moon A, moon B, and moon C. Or this is a 90-degree angle. Those three moons orbit 100,000 kilometers above the surface of a planet. So here's my planet. The planet is 20,000 kilometers in diameter. So I know from here to here is 20,000. How far is moon A from moon C? So I'm looking for this AC, right? Which I'm going to just call X. I know this part of it is 20,000, right? Because that is my right there. I know that A, B, and C are 100,000 kilometers above the surface of my planet. So from here to here is 100,000. From here to here is 100,000. And from here to here is 100,000. So if I want this entire thing, that's 100,000 plus the diameter, 20,000, my planet, plus the other 100,000. So I end up with 220,000 kilometers. That's how far Moon A is from Moon C. All right, so that wraps up section 10.4.